encountered mean field in their research, but maybe doesn't use it? Okay, so like, has anyone here never ever heard the two words mean and field other than like in this context appearing together?
Yes, it.
Okay, good. So, then kind of, this is like more like a tutorial and less like a formal lecture. So like interrupt me if you have questions or something isn't clear, if something is too clear and I'm repeating myself. And kind of like maybe to contextualize this talk, last workshop, I felt like there were really not so many people from a physics background. So when I was preparing these slides, I kind of had like a mean field for the physics uninitiated in mind. And then came to the workshop and was like, wait, but actually a lot of people do know mean field. So I was sad, but then I realized that actually everyone else kind of does very different things. So I'm just going to talk about like my view on mean field and how it can be used in neural networks. It is not trying to like make any definitive claims on the state of mean field and deep learning. It's just kind of how I use it. And if anyone has other thoughts on better or worse ways to do mean field, then yeah. So we made it to this point in the workshop, and I think we can all agree that neural networks are very complicated and we should really understand what they do. So yeah, that's like the motivation, but there's a lot of things that networks do, and they're complicated and that are interesting that we would want to know more about. And what I like specifically focus about in my PhD and will focus about today also is the process of feature learning. I think also the word feature has come up many times today, today and yesterday. And I think there are about as many definitions about feature learning as there are people that research feature learning. At least this is my impression. So just kind of like vaguely the agreement is that it's this kind of process that in the different layers of the network, you can learn functions or representations that ultimately help the last layer perform better on the task. So it's not like there's a bunch of random stuff happening in the depth and suddenly in the last layer you have this like eureka moment. You have these like intermediate steps that help you get to your destination more smoothly. Sorry. And I didn't say this, but my PhD is in physics, and I'm thinking of this problem like the picture I showed before. Like we have seen that feature learning is something that happens in neural networks, but I want to understand how it happens and why it happens, and not just like observe it from like an experimental point of view. So I want to have like a model where I can make like predictions about feature learning. And so like as the slides are, so I realized that, yeah, there's like a phase of one slide between what's here and what's here. So, so I want to be able to make like a simple model that's the spherical transformer and manage to predict this complicated thing that is the real transformer. But crucially, I want to like have something that connects these complicated models. Like it's not just like I could just do something super, super simple, but I want there to be like, kind of like, I think of it as like a bridge that I can continuously walk on from my toy model to get to the complicated thing. And on that bridge is feature learning. So I want there to be like, in my toy model to have the feature learning, even if it's simple, but I'm not necessarily looking for like, yes, I'm looking for like the simplest toy model kind of, which has feature learning in it. And I will define feature learning for the sake of this presentation today. And that will be that in my deep network, there is some representation in the hidden layers that depends on the target. And I think generally the intuition is that the labels are the target, like what ultimately we're trying to learn. I think generally we like to think of feature learning as a way of helping to learn the target. So this definition doesn't quite have that, but kind of like as a first step, we do expect that inside the hidden parts of the network, they will end up depending in some way on the target as a like something that maybe or maybe not useful, but at least this is like the 0th order feature learning that I want to have in my toy model. So that's like the goal. So yeah, then kind of like what I'll be talking about today is just background, which is going to be relatively long. Well, I'll talk about like the setting and what the needs are for mean field, which was the title of the presentation, and then how we can apply mean field to do things in real neural networks and kind of like a more straightforward canonical example. And then also, which is like the forward approach. And then the second thing, which is like kind of a paper that we put out recently, and I'll try to really do a step-by-step derivation there. Okay. This is the network architecture. Also, we've seen similar things many times in this presentation, but just like for the sake of notation, we start with some input X that lives in RD. Then you do a linear multiplication by a weight matrix W1. Then you get to this H thing, which is going to be very important. This is the pre-activation. Then you apply a nonlinearity, and then this will be the post-activation. And then again, a weight matrix, and this goes until the end of the network where we have the output. And the H's, the pre-activations that are important, and we will discuss a lot later, like the reason we can think of them as kind of like a reflection on what's happening in the network, the function that the network learned at the ELF layer. So after, because it accepts X as input and has some dimension as output, and this is kind of telling us like what is the function that is happening in the middle of the network. And then when I think there's like a lot of people in or were previously that do more like focus more on dynamics and how does the training, like how do networks change as like we train, and that's less the perspective that I am interested. I think of networks at equilibrium, so we train the networks like to infinity until they kind of stop doing anything interesting, and then we look at ensembles of networks that got to infinity. And then we think of like supervised learning with a labeled data set, and we train with Langevin dynamics, which is like gradient descent, and we add noise at every step, like this diagram on the bottom. And with quadratic weight decay.
With
the width, for each layer, it depends on the width of the previous layer.
Sorry, how much is that different from minimum sampling?
We do one one sample. The whole sample is doing gradient descent with noise. So instead of
that's what I meant actually. You know, it's isn't problem. It's what both are at the same and they're very small LR. Okay, for all of these. If you have a large LR, then like even full batch is still not exact.
We use a vanishing learning rate. Okay. And I will do a quick notation break. We can think if we're training on a data set of size P, so then we can have like some function, which will be our reactivations that go from input to some scalar. Then we can define a vector that has these P coordinates of the function applied to the samples as this like I never remember which one's Braun, which one's Ket, but that one. And then the transpose will be the other thing. And then this like lets us write inner products. And in neural networks, there's a lot of indices. So I like this way of writing it because it is somewhat cleaner. So since everyone raised their hands basically in the physics thing, then I feel like this isn't the first time you've seen this. But if it isn't, then I apologize. Or if it is, sorry. Okay, so because we're thinking of like training with this random noise that we're adding in every step, and we're looking at many networks, there'll be like a distribution of the network outputs. And the distribution looks something like this. So we have F that's a vector in the sample space that's on the training data, and we have this likelihood term that comes from the loss, which is just like normal, like F, just the MSE, e to the power of. And then we have this prior term that constrains F to actually being an output. So this is like a distribution over all possible functions that I can learn in my space, whatever, and then I'm constraining it to actually come out from a network. And also because I'm using quadratic weight decay, that gives me like a regularizer on the weights. And even if I would train without data, there would be a prior on what networks I could have. And then this term comes from that. So we have this likelihood and a prior, and then this thing which looks simple but is very, very complicated because this is very complicated. Like this is a nonlinear function of W in many layers. So all together, this is like going to be a very complicated object. And like if we solved it, then we managed to understand everything there is to understand about the distribution of this deep nonlinear network. And yeah, so the whole point will be to approximate this quantity. Are you okay? Because you look, okay. Yeah, so what we'll want to do, because we want to understand the feature learning, is we'll switch, instead of focusing on having an integral over the weights W, to having an integral over the pre-activations. There's a bunch of reasons why you would do this. Also because from the perspective of what you're learning at each layer and helping you learn the output, then that kind of makes intuitive sense. But also these H's are a matrix multiplication in it, so it's like a sum over a lot of variables, making it somewhat more regularized and maybe well behaved. So optimistically, this would be possibly a better quantity to think of rather than the W's. And so we'll actually do that. Okay. And this is the beautiful term that you get when you make the transition, is just introducing delta functions and integrating them out. And then you get, you can write the joint probability distribution of all the hidden layers and all possible functions. And it's given by this one. Does this thing also make slides go forward and backward? No. Oh, well. That's just a normal distribution, a normal distribution. And it's normal with respect to a kernel. So you have the pre-activations. They're normal with respect to a kernel, but this kernel is actually fluctuating and depends on the pre-activations of the previous layers. So this is the post-activation kernel, this guy, and that's the outer product of the post-activations in the previous layer. And this is going to be a very important quantity that's going to come up a lot. But because the kernel is not fluctuating and depends on the previous layer, it's not a normal distribution, and this is also very complicated and hard to solve, and this is what we want to be approximating. So this is kind of the prior setting, and then to go to the posterior, it's just easy. We just multiply by that likelihood thing that doesn't depend in any way on the hidden layers. So we can mostly think about the posterior, and then when prior, which is this part, and when we want to add the posterior, we just add this thing. So a lot of I'll kind of go back and forth between the prior and the posterior, and they're very similar to each other. So I think it helps maybe to think about it visually of what's happening in this prior. So we have all the pre-activations and all the different layers, and kind of working our way backwards, we can see that there's the output interacts with the labels Y through that term there in the green box. But it also interacts with the previous layer through this prior term that we got here. And then similarly, we have an interaction between the H's in the last layer to the layer before that and before, and so on. So you have this kind of bidirectional flow of information, where on the one hand we have the targets interacting with the F that interacts backwards, but then also the post-activations will interact with the next layer. And this should really resonate with the initial picture that we had of feature learning, of having the different layers helping the last, the network actually learn something. Because if I did something smart here with the H's, then these H's can somehow learn from this. And this is kind of where we expect to see feature learning coming up. Or we would hope that this model can capture feature learning. And yeah, so we hope that when we try to simplify this very complicated thing, we will still see this behavior. So one thing that we could do you all believe that this is hard to actually integrate and do anything reasonable with, right? Okay, great. Because this looks nice, but there's also log determinant stuff here, and it's not a nice expression at all. So we want to be simplifying this. And one thing that we can do that's the kind of naive, and at this point I'm not going to justify it mathematically or anything like that, but we can just say, okay, these phi's we're summing over the width, so if we take a large width, then they should just concentrate. And then instead of having this kind of interaction thing going on, I spoilered what happens. But instead of having a real interaction between each layer and the previous layer, it just depends on the mean of the previous layer. So now only the readout sees the labels, and everything else just sees the previous layer. And that's it. So I think this counts as no feature learning. And I think most people will agree with me on that statement, because nothing in the back of the network cares at all about the labels in any way. So this was too crude. Yeah.
like the sun there to feel the hump like that. So you're not gonna like it.
Yeah, at this point, I'm just saying, like, let's just take I'm not justifying it. I'm just saying we took a very big width.
Relatively to the, I might ask you how many samples do you have?
Again, like, this isn't like a rigorous, I'm not thinking now about the scaling of the samples. So I'm just saying, like, very naively, it's a large number, maybe it will concentrate. There are like subtleties, and you have to take the limit correctly and keep the sample size constant, or do whatever other things if you want this limit to be exact. I'm just saying, like, let's think of toy model, of like approximations that we could be doing, and this is one of them, and this is the result that it has, and in certain limits it is accurate. But for now, I'm like just kind of I want to say we should do mean field approximations. So this is a bad approximation, and we need to do a better one. Even though, does anyone here, would anyone call this a mean field approximation? Just out of curiosity. Okay.
You're assuming that you're just taking the prior until the last layer.
That what?
You're just looking at the prior until the last layer.
I mean, I'm just saying that because phi is a sum over many things, then it will concentrate on its average. It's a semantic question, not like whatever, just, yeah.
So, but phi is the t-shirt.
Yeah. That's on the bottom.
Here you're saying you're also assuming that phi is just given by the prior until the last layer, or you're no.
Oh, like it's calculated, the phi with a bar hat line on top, you mean? Yeah, that's just calculated it's calculated according to the distribution of the h's, which will depend on the kernel of the previous layer. But just the kernel, not the...
So you're assuming that that's not from the target, from the what?
I mean, I'm not assuming. It's what comes out from making this approximation.
Yes.
Yeah. Yeah. So no feature learning. Our bridge is, this isn't going to bring us to where we wanted to go. Okay, so just a quick break to remind us about the Ising model. So we have the spin distribution, which is given by this expression. Has anyone here not heard of the Ising model before? Okay, great. So just I want to have like something to ground us when we talk about like mean field approximation. So this, I think we can all agree, is a mean field or approximation. And what we do for each spin is we take like the spin being its average plus some delta correction, and then expanding into leading order in the fluctuations. And then we get like have this, and then we get a distribution that factorizes, and we can do things with it, and it's analytical, and everyone's happy. And then we require self-consistently that the S bar is actually the average that we wanted it to be. So that's, I just want to maybe say before I continue that I think it's interesting, like at least my experience here so far, the many ways that people have used mean field in a sentence. I don't know that I use it the right way objectively. Like, I think I do, but if anyone, so I'm not like, open to discussion. I will just, if you think I'm really wrong, like tell me, but kind of, I feel like sometimes you can get into your own bubble of how you call things, and then you're alone in that bubble. So please let me know if that is the case. So going back from the Ising model, which we all agree is in fact mean field scaling, then here's some, this doesn't really look like the Ising model at all, but there are things in common. So like in the Ising model, we had interactions between neighboring spins, and in neural network, we also have interactions between these phi kernels and these h's. And since the Ising will result in like factorization, then we would hope that after doing mean field approximation on this setting, then we would also get a factorized distribution that will be more pleasant to work with. So that's kind of like the goal of having some kind of approximation like this. Okay, so I'll start with like a kind of straightforward, or I think it's straightforward way of doing mean field. I call it forward not because it's more in contrast to the second way, which is inverse. So this is just regular, Okay, but basically we have this posterior distribution, and we have our h's that are coupled quadratically to the kernels, which also appear in inverse and are complicated. But basically what we can do is just say that we have this capital H kernel, which is just the sum over all of the pre-activations in transpose. So we have, and then that will assume that concentrates around its mean, so H plus delta H, like in the Ising spin, and also for the post-activation kernel. and we'll take this as average plus delta. And about the scaling, yes, this isn't necessarily mathematically correct, and kind of there are going to be limits where this isn't a fair to. Oh no, I guess not yet. What I wanted to say next is then we'll do a Taylor expansion, and that isn't necessarily mathematically correct. But this is just like I don't really want to get into that, so this is what you can do, and you might not always want to do. But essentially, what we're going to want to do here is expand this term up to first order in the fluctuations of delta H and delta phi, and this will also because this phi appears in inverse, and it's a full-on Taylor expansion in these fluctuations that are small. So that's the approximation, and then this is the result. And although it might not look like much, this is actually not look simple. This is actually a nice result. We have indeed, not surprisingly, that our distribution is factorized. We have the output distribution and all of the hidden layer distributions. And within each layer, each of the distributions, they're the same for all of the different neurons in each layer. And this is the output distribution, which is just Gaussian with a lot of...
You mind with pi states?
What pi? That's just the posterior. So the distribution of the F after training on the data. Yeah. So this will be Gaussian. And in each of the hidden layers, we have a not Gaussian distribution necessarily that's given by this expression. And the nice thing we can see is that we depend on the previous layer's average, but also on the next layer's average. So let's break this down a little. We have this Gaussian-like term, which depends on the previous layer's average. And then here are the activations in an inner product with the next layer's kernel and this layer's, but we depend also on the next layer and also on the previous layer. And that was what we had wanted, because this, if we go back to the last layer depends on Y, but then this layer will depend, sorry, not this layer, the L-1 layer will depend on Y through this term. And we have exactly what we were hoping for, which is a simple model that does capture this relationship between all the hidden layers and the labels. So this is maybe the simplest thing that you could do that will result in feature learning. Don't quote me on that. I'm not sure it's actually the simplest, but I feel like it's a first order Taylor expansion. So, and the last thing is we need to solve the self-consistent equations. And this is kind of the hard part of this problem, because we have these, we have to calculate the expectation of the activations of H, which is not linear. And this is a P by P matrix, which is large. And then we're calculating the expectation with respect to distribution that depends on this quantity. So this is a very complicated equation. And yeah, same for this. And this is kind of the hard part about the mean field approximation, or qualitatively we do see the feature learning that we expected to see, but actually calculating with that correction here is not going to be that easy. So we are going to need more approximations, and I won't really go into that. It was more just a qualitative demonstration. Yeah.
Just we even do have exact solution to this testing equation to get what is the attention for this search.
I think that maybe getting the exact solution is less intuitive than doing more, because in the end, if you do the exact solution, okay, so maybe let's think of a simple case, which is a linear network. So now these activations are linear, and we have just H and H. And instead of having a kernel, just the kernel, we have something like the kernel becomes, because this is with a minus and this is with a plus, so the kernel becomes smaller. The inverse of the kernel becomes smaller. And then this means we're going to be shifting. Well, yeah, I'm not sure how. Maybe I'll actually give a simpler example than that. Not simpler. I will use the approximations that I said will be more helpful. But what you can do is, sorry, I was thinking about the best way to. Okay, so let's say that we have that it's Gaussian, and now we have a H, and let's say that I actually don't think it's going to be that helpful to go into this in that much detail on second thought. No, because I'm not going to really go into them in depth, but in the second half, we'll go back to this. Okay, but I'll briefly go over some approximations. I did a mean field approximation with an order parameter or some order parameters, which are the kernels, but you can do other order parameters that maybe are more less large. So like the Lienson-Polinsky paper and that Pacelli paper, which is an extension of that one to nonlinear networks. And then this is a nice approximation that instead of, if you take the limit of large data size, then you can replace the sums over data points with integrals over the measure. And this is really like what makes these expressions sometimes a lot more legible, because you can actually solve the integrals analytically, and then you see really nice things coming out. And there's a lot of, like in my group, we do that a lot, but didn't actually cite the paper about the approximation. But, and then...
But to do that, you need an analytical version of the measure?
Yeah. You need an analytical version of the measure, but then you can also do some tricks even if you don't have the analytical version of the measure to like approximate an analytical version of the measure. But yeah, you'll need an analytical version of the measure to come up with an analytical expression. But you can also like, if you don't want to, so this limit is saying you have continuum data. So that's a pretty strong assumption because you're not training on all of the data in the world, but you can also take this effective, the data averaging method, which is like saying, I don't have infinite data, but I'm averaging over all possible outputs from all of the data. Like I'm training over a finite size of samples at a time, and then averaging over what my prediction will be over all of the samples that I could be taking. And then you kind of get the same nice things that you get from the continuum approximations, but you need to do some more corrections and stuff. So these are all like tools that can then make this complicated expression that we had for the posterior be something that we can handle and then come up with intuitive results. And also like the Grokking paper that we got that Dimitri was saying. So this is all things that we can do from here. Okay, so I also wanted to, what time is it, by the way?
4:04.
Okay. I also wanted to go over some of our more recent results. So this is what I call like the inverse thing, because instead of saying like, we have this posterior, let's see what we can know about the system from the posterior distribution, it's going the other way around and saying, I'm going to assume something that I actually managed to learn the target, and then what will happen in the network, assuming that I managed to learn the target. And then this is, so yeah, that's from a paper in ICLR in 2 weeks. If you'll be there, come say hi at the poster. But basically, you can show pretty easily that if the, there is a typo here. Sorry, this would be there's a likelihood missing. But basically, the posterior is like upper bounded by e to the power of the sample size and the prior that f equals y. And I can think of f as really like a function over all of the truly we managed to generalize, and that the output of the network will always be y, assuming that we have some well-defined y that we know what it is, and like not like cats or dogs. But then we can say what is the likelihood, the probability in the prior that the network will always know the labels. And then this is just the number of samples that we trained on. So the prior probability, the random network will manage to generalize well on some function that I chose is going to be really, really small, right? Is a random network? Yes. And then to like compensate, so this is like very not likely to happen. So then we would need a lot of samples to make this not upper bound by 0, right? We don't want our prior to have an upper bound of 0 because then we won't learn the target. So if we have a lot of samples, that will like cancel the very, very low probability of this event happening. And it's kind of like the intuition. And because we're thinking of like these low probabilities, it lets us use all of these like tricks from like rare event. And in particular, the most probable network that manages to do in the prior that will manage to do f equals y is going to dominate the probability of getting f equals y. So we can think of like in the prior probability, there's all kinds of different random networks that can represent the actual function that I want. And when I train, I just kind of select the most likely of those ones. And I won't manage to access that one if I don't have, like, the more rare it is, the most likely one, if it's still really, really rare, I'll need a lot of samples to kind of access it during training. That's like the intuition. So if we find the most probable network from the prior, then we can say, like this will give us some like information on what will eventually happen in the posterior, or at least the most likely thing. So then we have this like method of how to find this, and it's at this point it's not very like the goal isn't to actually find an exact prediction. It's more to get like a scaling behavior, or at least to like rule out impossible events. So the first step is to consider, and I guess I'll also add, because of the like mechanistic interpretability people in the audience, that this is kind of like bridging a more theoretical, like first principles approach and a more mechanistic interpretability approach, because we kind of take what we know about how networks do feature learning and generalize, and we're like using that knowledge to then apply to building it from bottom up. And so our first step will be, let's choose from the many ways that we know that networks do feature learning in the wild. Let's choose a few options that seem reasonable for the task at hand. So like, what features do we think are going to be useful for the network to learn? Maybe like, let's learn first an easy feature and then a hard feature in later layers. And specifically choose types of like methods of things that we have seen in feature learning that other people have observed, like in previous experiments or whatever. So we choose like all of the like ways for our features to be represented in the network. And then we can propagate these through the network with mean field propagation, and we can see how likely it is for each of these features to happen. So I'll explain what I mean. We can choose like a distribution for the first layer, for example, and then this will give us a kernel. An expected kernel, if we chose it like by hand a distribution, we can calculate what the kernel of that layer will be. Then we can see how likely, so this is like going to be the definition of the prior distribution, and we can see how likely the next layer is going to be given the kernel that came out of our choice for the pattern for the previous layer, and then we can select the network that came out as most likely. Was that kind of clear-ish?
So the red C, what is
that tells me the circuit. Like, it's not the regular average, like it depends on my choice. It's not like it doesn't come out of some self-consistent equation or anything like that. It's like I enforce this kernel into existence.
How did the circuit give you this kernel?
So the circuit gives me, I choose a probability distribution. I'll give a real example and we can go through it step by step. But I choose a distribution of H's, and then the kernel is just the expectation of the post-activation of these H's. So because I chose the distribution, I can then calculate that expectation. And then I can see how rare it would be. Like if I chose well, then it will like help the next layer do whatever I want it to do. Doing something that will be very far away from this will be very unlikely, like from this normal distribution with the previous layer's kernel. But if I chose my features well, then by learning the features in all the middle layers, then this will actually become easy. Like for the readout will have all of the ingredients that it needs to compute the right function in high probability. So just like
this could tell you whether you found the right features or the right circuit.
Yeah.
So this is what you're doing equivalent to saying, so you kind of like fiat the kernel of every layer, and then you then separate check to compute the effective free energy of the early layer kernels, but then you only look at the last layer in your regression and see if it's likely, if it increases.
No, because I calculate the probability of each of the layers happening given the current, like.
Yes, so you are actually computing the entire effective free energy of this collection.
Yeah. Yeah, so kind of like how the mean field comes differently in these two methods is in the first one, or the forward one, we, by taking mean field, we like allowed fluctuations in these phi terms that gives us this, and also like fluctuations. And basically we have like, this is coming from the comes from the fact that we allow fluctuations around the kernel and not just make it concentrate around its mean. Whereas here, we're baking in the fluctuations by taking a distribution that is different from the mean. So we are handpicking a distribution. It's fluctuating in the sense that it's not the mean, not what we expect the mean distribution to be, or not necessarily. And then this also gives us a kind of like mean field. This is a more loose mean field than the previous one, but still we are taking things to be concentrating, and that propagates, like each layer will only depend on the average quantity. So that's like the mean field flavor. And I'll give an example, and I think that this will help explain what we do. And so it like really stop me whenever something becomes unclear. So we're going to have a 2-layer network with error function activations, and our data is going to be IID Gaussian, and the target is the third Hermite polynomial, which is x to the power of 3 minus 3x. It's nice because it's a natural function to use for the data distribution that we have. And we're going to think of 2 types of feature learning that can happen, or not feature learning, like circuits. One, nothing happens at all, and the last layer does everything, and that's like what would happen at infinite width. So this is the lazy pattern. And the second one is the specialization pattern, where most of the neurons aren't doing anything. But we have one neuron that actually figured out in the first layer that it should be learning the linear function. This is something that makes sense to do. The linear function is easier than the x to the power of 3. So it makes sense to start from that and not directly from the final answer. And one neuron, just because we'll start with one and then we'll go to more. And there are other patterns, and like in the paper, we do have more things that we can consider, but just like for simplicity, we'll think of these 2 patterns for now. So these are so then let's start with and I will go over this again, that we don't actually care about factors of like 3 or 10. We're like interested, the thermodynamic quantities here, like the dimensions and the sample sizes are what is interesting to us, and not so much the small numbers. Otherwise, it's going to be very difficult. Okay, so the probability, if you remember, the prior weight distribution is just e to the power of minus d in the norm of w. So if we're looking at our one specializing neuron, what will this exponent be? If it's just w star dot, it should be 1, right? Because the norm, I guess I didn't say that. But the norm of w star is around 1. We're like learning a reasonably sized function. So this will just be minus d in the exponent for our specializing neuron, right? And the rest of the neurons, they're just sampled from the normal distribution normally, and they're going to be sampled with probability 1. And if we want to calculate the post-activation kernel, so this is a little more, I'll do this a little more slowly. We have almost all of the neurons that we're just sampling from the lazy Gaussian process infinite width distribution, and one neuron that we're sampling with like a delta function. We've forced it to be exactly the feature, so it's just going to be this outer product of the activation of the post-activation of that, like, there's also a typo here. There should be like a star, because that's our feature one. So it's like our special feature. It's not drawn from any, So that's going to be our kernel. And if we want to calculate the probability of the output, so I'm a little bit cheating here, but it's not, anyways, so we have the inverse of the outer product of the function, which we wanted to be y, on this kernel, which I just kind of rewrote here a little bit. And now this product, the sandwich thing, is an integral over the data measure, because we can take y to be a function, we can define the data measure, and this result is just standard, and it's 1 over d to the power of 3. And this, so if we took error function activation, we can just write it in the basis of the Helmholtz polynomials. So the inner product with the third Helmholtz polynomial will just be like 1-ish. So we have 1 over n because we only had 1 neuron. And we have, this is 1, and this is 1 over d to the power of 3. And then in total, so we have from layer 1, we said that the probability of that happening is minus d. And in layer 2, given the pattern that we chose for layer 1, we have this 1 over n term from this guy and 1 over d to the power of 3 from this guy. And all together, we have that the probability of this happening is this expression, which you can see that for like for assuming that n is not as large as d to the power of 3, then this is just minus d minus n, so it's like linear, and otherwise then it's going to be just n. Yeah, I guess I have the slide. Yeah, sorry. And on the other hand, so I'll just go over again kind of roughly what we did, which is like we found the probability of our pattern for the first layer happening, then we can calculate the kernel based on that pattern, and then we see if we, given this kernel that the first layer gave, what is the probability of the output being y in the end? And then we get that the total, like we multiply these probabilities and we get this total expression for the probability of our pattern emerging under this approximation.
Your scaling is like PTP, but it's like between n and n cubed, right? Or say it's like you're scaling NGP, but your width, the width of the input there becomes a large variable that like, and now depending on the relationship, right, it will either be GP or for what you were, right? Because if you take n to actually be infinity, right?
Yeah, exactly. If you take n to actually be infinity, then this is less likely now. Yeah. So if we do the lazy circuit, then we're drawing all the net weights from the prior. The probability of that happening is 1. The post-activation kernel is this is GP kernel, and then this expression is just the standard result that we have from the GP. So this is minus d to the power of 3. Yeah.
Can you explain again how did you choose the distribution, the prior distribution?
So this is where I use my mechanistic interpretability hat, and I say, I trained a lot of networks, and I saw what they did in previous papers that we wrote, and have some kind of intuition. And also, like, I can think of what will a neuron reasonably want, like a feature reasonably want to do. It has not many options. So like there's a cubic target. There's one feature that is interesting, which is the W star X feature, right? Anything else isn't interesting to it. Maybe it doesn't, but it doesn't feel like it would be a good idea. So I wouldn't like try to force that on the network.
But it's playing, like on a lower level, right? Like you use that every neuron is a row of the linear matrix, and it can read. So every neuron reads the linear direction of the input, and so the model here is that either some neurons are just random, so they just kind of there for it to mesotropy, and some neurons are there. The specializing ones are just aligned with the direction that you care about. I guess I'm quite like I guess I understand that points, but multiple question remain, right? Why only fix one hump? Why?
We're gonna fix more than one neuron in a second. I just wanted to start. Yeah, I'm starting with one because just I feel like it illustrates it a little better. But yeah, and there are other things that we can do. We talk about that in the paper, but yeah, in principle, you can do many things. And in the end, the answer isn't like, it's not saying for sure this pattern is going to happen and not the others. But at the very least, if our it's more likely to yes, have feature learning than to not have feature learning, which is also like a useful, yeah.
Well, question number 2, that's probably the more important one is like, what fixes the noise and always the assumption. So the rest of the
by default, there's like this trade-off between the prior wants everything to be Gaussian, but for the network because this is the prior, like the prior distribution.
From the fact that we initialize in Gaussian way, or
So we're thinking we're not really like, we don't care about the initialization. It comes from the choice of weight decay. We're looking at what happens in infinity. If you
so your lot has a term that's norm squared, weight norm squared.
right, so that's yeah. And you can think of it as like what happens if I just do weight decay and I just walk around the lost landscape of just doing weight decay with noise. So it's not a trivial answer.
Right. Okay. What is D?
D is the input dimension. And if we want to have M specializing neurons, so we can say, okay, then in the first layer, we just had the likelihood of one neuron is M, so that we multiply that by M. And then in the second layer, also we had we just add here the number of neurons that have that like specializing value. And then in total, we get this expression instead. And if we take this is really large, again, we'll recover the same result as a lazy case. And otherwise, we can choose the best M, so the M that will give us the highest probability, and that is the square root of N over D.
So by having specializing neuron, there are M neurons. Each one of them have this.
Each one of these learns the teacher. It learns the feature that we want to learn up to sign.
Okay. But there's an alternative way to do it, which is to distribute the teacher across N1 on some coordinates.
Yeah, each of them learns like 10% of the that is a way to do it.
Change anything or just the same as that?
It will change things. We do have that in like deeper networks, that we see that it happens in deeper layers, that things do like that, but that's like
It doesn't happen because this has worse, where instead of the two ridges, the only ridges are either you're completely free or you're saturating because you have a bounded equity.
Yeah. Anyways, after we do this, if we do use this optimal M, then we get the square root of ND scaling, which, in the end, which means that, no, that was not M equals, that was a typo here again. Basically, if we take the N to be near the scaling of D, then it means that we'll have, if N is smaller than D to the power of 3, then this will be even more likely than the other option. Okay, so then some results from the paper that we have. So first of all, you can see that as you you can actually calculate the distribution analytically. That's the dashed line for 2 layers. It's possible, but we can ignore that. That's not relevant to here. But if you look at this yellow line, then this is the negative log distribution of the inner product of the activations and the linear feature. So this is saying how much of the hidden layer pre-activations are aligned with the feature. And here, most of these are not so aligned, but we have a few in the edges that are very strongly aligned. So these guys are learning the feature in the yellow and purple curves, and the rest of them are kind of doing these are the not specializing. So this is where the M neurons would live if there were actually M of these. And if you actually count how many are living in these minima, then you see that this which is this y-axis here, then that scales with the N over D, which was what we predicted for M to be exactly. The nice thing about this is it's because this approach is pretty simple, and we can really scale that to a lot of different types of models and deeper networks and CNNs and transformers. And what else did we do in the paper? A bunch of things. But I think that this is a useful way of using intuition that we can gain from actually looking at networks and what they did and how they trained, and combining that with the equations and theory that we get from a more rigorous mean field view. Yes.
So the intuition that's diagonally falls, the alteration that there's subset of neurons that are aligned with the teacher that you see after it, and that's what leads to this sort of choice.
Yeah, but also in linear networks, for example, then we can also say that there's instead of having a Gaussian has something that looks a little more like this, which is a wider distribution, we can also use that. Like the circuits that we choose, as long as we can calculate the kernels or at least vaguely approximate them, I can choose any distribution that I want to. Like it can be the specializing type of thing, or a Gaussian, or what you said about them being divided over many smaller fractions. Like I can, if I can compute the kernel of that even roughly, then I can do whatever I want.
What's the actual, like, what do you spirit? What's the scale? What goes to infinity? Is it like n?
So yeah, so here we're taking standard scaling. So like not just n going to infinity. But yeah, sorry.
So you take both n and d.
Yeah. So it depends what you're trying to say. If you're trying to say when will you move from one regime to another, it's just increasing n without d.
I mean, so okay, but and you go to infinity together.
Yeah.
And then, so you find that the free energy difference between the specialized and unspecialized probability is like 1 over n. Otherwise, I'm not supposed to ever see both at the same time, right? Because like one is exponentially more active than the other. So like you would, supposedly I have my probabilities region that has 2 minima, right?
Yeah.
Specialized and one not specialized.
Mm-hmm.
And the free energy between them has to scale like 1 over n. Because if it's like order 1, then I put in an exponential times n, and then I will only see I would only ever see one of them. Right.
I think that there's multiple minima, maybe that I'm like in general, like over the whole lost landscape. You mean that there are multiple minima, or
some of the one min. There's one minimum, but the minimum.
I don't think.
I don't think that's just true. That's true. Just a second one minimum. Okay. Because as far as it, like you assume there is a single distribution for all the neurons, right? I mean that's the IID, or is there a conjoint distribution?
So when we choose a pattern, we're not specifying that we're choosing for each neuron what its distribution will be. But when we compute the probability, like I'll go a few slides back. Okay. Like when I choose a distribution that is not IID, like having M specializing is a not IID distribution. Like I chose specifically for 5 of the neurons that there'll be something and the rest of the neurons will be something else. But when I want to propagate how rare that would be for the next layer, I substitute it in this expression here, which is IID, in the kernel of the previous layer as an approximation. Does that make sense to you?
Not yet.
Like, I'm forcing, like, by choosing these patterns, I am forcing a distribution.
Yeah, but...
And what? And then the next layer, so I force a distribution for layer 1, and I can calculate how likely that layer is according to the GP distribution. This will give me the probability for layer 1 coming up. Then where the mean field enters is exactly here. Because I force this distribution, it's like the fluctuation corrections to the GP kernel, but then that kernel will propagate to the next layer. And when I have my fixed pattern for the next layer, I calculate how likely that fixed pattern is given the previous layer's kernel. Substituted in here, in a Gaussian IID distribution. So I'm choosing a not IID distribution. Like 3 neurons are doing one thing and 5 others are doing something else, and they're completely not correlated or correlated in a complicated way.
Right.
I know, right. So but this is the actual probability. This isn't like, there's two different probabilities. There's my circuit that I chose. I chose it with probability, and then there's the probability of that circuit happening in the network. When I calculate the probability of that circuit happening, I calculate an IID. But my probability, just the word probability is bad. My circuit is not an IID probability because distribution.
But you pretend it when you calculate the
No, because it maybe
depends on the probability. The kernel depends. Okay, maybe I'll ask you later.
Okay. No, I'll try one more explanation to see if that helps, and then we can move on. But I am fixing, like the meaning of like a circuit means I'm fixing a distribution from which I am drawing the h's. Yes, we agree on that. And then I can calculate what the probability is that the prior drew h's from that distribution. The distribution I fixed is not IID. The prior is IID. The kernels will depend on the circuit, but the prior is IID. Okay, so there wasn't that. Yeah. Oops. That's it. So any questions or? So I'll start with that question and then answer the multiplicity one. It entered here because I know how to calculate this kernel and I know how to calculate the inner products, at least approximately. So the choice of the activation and the choice of the, like the fact that we draw our data IID Gaussian means that choosing it to be a third order Hermite polynomial makes this like a convenient object to calculate. That is one, like, and the other thing is that because, and I guess like kind of similarly, because I can write my activation as an expansion over all Hermite polynomials, then the inner product with y is like a clean trivial thing. Like for example, if I would have wanted to have y that had both a linear and a third order component instead of just, so like just a linear function, for example, instead, this would no longer become necessarily the most likely pattern to emerge because it has like a lower order product with the, like this, I guess this term will be the culprit here, that there's a lower, it's easier to this is smaller for a linear y. If
I'm saying that if you change the input-output relationship, that expression, that whole expression, the Helmholtz curve, the expression in the exponent will change.
I'm not sure I understand by what do you mean by input-output relationship?
Y equal to x.
Oh, why the output? That's not this relationship is just this is what I want to be the output, and this is what actually is the output. So I'm forcing the output that is coming out to be the output that I want it to be.
Yeah. So if we change that to not for it, but put.
If we change this y to be something else.
Yeah. What will change on this?
Just the calculation. Like it wouldn't be the same answer. Like it will be. We'll have to choose other. But the actual math that we do, the form is the same.
Okay.
It's just how we calculate it is much easier. And also what we can say about this term.
How we calculate? Sorry, the final line will change.
The final line will change. This line is still correct.
Yeah. Okay.
And the numbers here, basically the numbers that we plug in will be what changes. And to answer,
Oh no.
So I'll just answer your second question about the multiplicity. Yes, that is you will get multiple things. We found that like even in this setting, like if you set d equals to n, then both of the answers, then this, well, I guess not both of the answers because I didn't give you other options, but some of the answers look like they will agree, like you'll get the same result, but they will have, if you can scale like some of the parameters in a way that will then point you to which the correct one is. So like, let's say I'll have So I'll have like one expression that looks like a square root of dn, and then another one that's like d n, and this will be half, and then this will be, I don't know, half, so that if we choose d equals n, these are both going to be equal. But by increasing n, we can see how like the dependence on each of the scale all of the different variables that our final expression depends on, and then it will give us an indication of which is going to be more likely. But also, like, we're kind of okay with multiplicity because we're not necessarily, like, we're trying to point towards, is feature learning going to be more likely in this case, or what modes of feature learning are possible? This whole thing is an upper bound, if you remember correctly from a few slides ago, so we're just trying to make it not impossible to learn the target. So if there's two methods, that's kind of okay. We live with that.
This doctrine of the coming out as Pablo.
And what?
This doctrine of them all coming out as like Pablo.
Yeah.
Okay. Yeah. So So what you were saying towards the end put into a issue in my head, and I just wanted to see if this is at all or everything back. If this like choose a circuit and work out the probability of the circuit thing, reminds me a little bit of variational methods.
Yeah, there's a lot of variation here. Yes.
Yeah, like so, like the sort of thing of this is like quantum many-body stuff where you say, oh, okay, I can't find the actual ground state, but I can guess, and so that's number bound.
Yeah.
Is this like a spiritual lesson of that?
It's like I gave the like result of the paper, but the derivation is using exactly that. So that's, yeah.
So should I understand that this like log TFL is like the number of samples that is
Yeah, exactly. Yeah.
will be needed to learn the target if I assume that I'm using specialized.
Mm-hmm. Yeah, exactly.
So I guess this is like for this specific target function. I could also say, okay, I'm learning with a matched architecture that doesn't have all these layers and all these skills, and I can also in that case. So my question is that how does this compare? So here, what is the advantage of having many neurons? In a sense where I could also compute the same threshold, but the threshold sample to learn is like single index model that you have with just an architecture that is matched with like one.
Like a teacher-student that is the same architecture as a teacher and the student, I think like this isn't necessarily saying like it's an advantage or not. Like there's no reason to use this model. Like for each model,
It's asking how does how many thresholds should I explain the threshold that you're saying that if you have a matched architecture?
I think it's going to be very different. I think we kind of do we assume here that the width is very large for the approximations to be accurate. So I don't think we could take if there's a single index model, then that would like break a lot of our assumptions. So I don't want to say anything about that because it's like
I can say one thing, which is that there's a polynomial comparison. So if you specifically in mean field, the somehow minimal number of data points that you need to learn the mean field limit, there's a polynomial bound in both directions. Well, maybe this is at fixed D, at fixed width, but like there's a pair of polynomial bounds on how many like take over all possible width, the minimal over all possible widths of how many data points you need to learn. That's both bounded above and below with the polynomial of the minimum number of data points you need to learn at the event. This is
not our result.
Yeah, this is our result. That right. No, but there's like a very simple argument. And there's one way to make this argument very simple, especially when you could tool it. So lapsing into the realm of the fantasy, but going lapsing also into the subject in this workshop. I wonder, it feels like almost tantalizingly write downable to think like, oh, okay, my model, my agent, whatever, like could solve a problem this way. Treat this variational ansatz, and then I optimize it to below some loss. It'll find something that cleverer, or something. I don't really have a question here, and this is it's just like, I guess we're all here in the church are bridge. These ideas and like, this sort of mech-interpy thing. And I don't know, I was wondering if you or really anyone has thoughts on, I don't know, like, if this variational idea can you apply for like an ansatz or there's some, HB here or like some other circuit.
I mean, we're definitely, like, this is like a lot of, like, we kind of came up with this and now we're trying to see how far we can stretch this idea. We're thinking of like RL systems and like doing networks that are significantly more complicated. Yeah, I mean, I would say ambition is there. But yeah, that was good marketing. Thank you for the...
You got it. yeah, like I guess like similar to traction like I have before, which like have is there a way for this to formalize slash task slash multiplied so the linear absolute division have options
The linear what?
they can come up first in fact that features are linearly representable or so you can imagine solving this for under the assumption that the I find it out model find out the sort of improper relationship in which the now linear version is like not just a dot product of some sort of curve level is intuitively have low free energy than into exterior and chat with lines.
I mean, yeah, I think the currently like our issue or like it's both an advantage and a disadvantage is that we're trying to really do things like I can write this on a whiteboard. Like I didn't, other than this thing that you had to trust me on, like everything else is like really simple calculations. And that kind of limits us to like a very specific class of problems and not so much like a big model that is complicated and has strange manifolds.
You stick some efforts to solve that persistent equation stuff.
We have a method and we have expressions for like this. I just didn't present it here, but we do have like expressions for kernels, like an equation, like a variational method. And like in theory, we can do more complicated things. Now our focus was more having it like pen and paper level of calculation. So we didn't do anything like that. But I do believe that in theory it's possible. And I think that like it could be a very reasonable track of how we think of comparing. Yeah.
So there's a shift with thinking about these first methods in the atomic unit that was providing separability, right? So we're not thinking about features, we're thinking more about circuits or like distributional methods.
Yeah, this method is not linear, like nothing perfect. So the kernels, they kind of sound linear, right, but they're actually function valid. Like, yeah.
And also if we go deeper, for example, like a result that we have is if we add another layer, we learned the linear feature in the first layer. Now the second layer can do nicer things, so it learns the not linear feature. But if we then you can kind of see if you shift the width ratios, then actually it becomes more worthwhile for the second layer to learn things without the first layer. But that's kind of the limitations of having a pen and paper level framework.
We should get after. It's on my